Today we are walking through program as weights-a programming paradigm for fuzzy functions.
Start with the motivation. What problem is this paper trying to solve?
The paper is about fuzzy functions tasks that are easy to describe in natural language, but awkward to write as exact symbolic code. Examples include flagging urgent log lines, repairing malformed JSON, or ranking search results by intent.
So developers already use large language models for that kind of fuzzy behavior. Why is that not enough?
The paper argues that calling a remote large language model for every input is convenient, but it makes the software expensive, dependent on an outside provider, hard to reproduce after model updates, and not truly self-contained.
What replacement does the paper propose?
Instead of asking a large model to solve every input, program has weights asks a compiler model to run once on the function specification. The compiler outputs a small neural program, and a lightweight interpreter reuses that program locally for later inputs.
On this diagram, the split is between compile once and run locally, right?
Exactly. The expensive part is tied to defining the function, not applying it. After compilation, the neural program is just a reusable file that can be cached, version controlled, and loaded like a library function. The paper formalizes that idea with a compiler and interpreter equation. A user specification, written as S, is compiled into a program P. Then the interpreter combines P with a new input X to approximate the desired fuzzy function f of X.
What is inside the compiled program P?
Program P has a discrete part and a continuous part. The discrete part is text-like guidance. The continuous part is learned adapter weights.
How do they build those continuous weights?
Their strongest implementation is text-to-ORA. The compiler reads the function specification, a pseudo-program, and learned prefix tokens. A mapper pulls the compiler hidden states, turns them into mixing coefficients, and composes low or high adapter matrices for the frozen interpreter.
So the mapper does not store a separate full adapter for every task.
Right. It learns shared lower A bases and predicts how to mix them for each function. The equation says each per example lower A matrix is a weighted sum of reusable basis matrices, with different coefficients for layer, module, and basis index.
What did they train this compiler on?
They build Fuzzy Bench, a 10 million example dataset of tuples specification, input, and target output. It covers 7 high-level families, with Cortex processing and natural language processing as the largest family at 30%.
Why does that dataset matter for the claim?
Because the method is not just prompt engineering. The compiler has to learn a mapping from specifications to reusable programs across many test types, then generalize to held-out fuzzy functions.
Now give me the main result.
On Fuzzy Bench, a 0.6 billion parameter Q13 interpreter running PAW programs reaches 73.78% exact match. Direct prompting of Q13 32 billion reaches 68.70%, while needing roughly 50 times more inference memory.
That is a smaller interpreter outperforming a much larger prompted model.
Yes, the key is that the big model is no longer solving every example. It acts like a tool builder. After compilation, a small frozen interpreter plus a task-specific adapter handles repeated calls cheaply.
How do we know the compiler-generated adapter is doing the work, rather than the base interpreter being strong by itself?
The ablations remove the compiler while keeping the same base model, data, and training budget. PAW beats full fine-tuning of the 0.6 billion interpreter by 15.4 percentage points, and beats the strongest fixed lower A baseline by 21.7 points.
Did they compare different ways to represent the continuous program?
They compare an earlier prefix tuning version against the low RA version at controlled scale. Prefix tuning reaches 50.4% exact match. Lower A reaches 56.5% at the same program size setting.
What happens when the specification is messy, like real developer text?
They test noisy specifications with typos, grammar errors, ambiguity, formatting drift, terse phrasing, casual phrasing, paraphrases, and combined noise. The point is to check whether compilation still works when the function description is not clean benchmark text.
The paper also claims local execution. What does that look like for a developer?
The developer interface turns a specification into a downloadable program file. After the first download, the user loads it through a small Python or JavaScript API and runs future inputs locally, without external model calls.
Is the local setup only theoretical, or did they report concrete runtime numbers?
They give concrete numbers. A Quantus Q13 interpreter runs at 30 tokens per second on a MacBook M3. The shared base is about 430 megabytes.
What is the main limitation or caution I should keep in mind?
The result is strongest for the fuzzy function setting they define and train on. The paper shows broad benchmark coverage. But the paradigm still depends on compiling a clear enough specification and on the interpreter being capable of the target output format.
So the takeaway is not just smaller inference. It is a different way to package fuzzy behavior into software.
That is the core idea. Program as weights reframes the foundation model as a tool builder. Compile a fuzzy function once, then run a compact reusable neural program locally. The headline evidence is higher exact match than DirectQ and 332 billion prompting, with about 50 times lower inference memory. That wraps up this paper walkthrough.